Linear transformations. Now that you have learned about geometry, let's see how we can transform it. So in computer graphics, when we have our geometry, we want to be able to make it smaller, larger, move it around, so that we can construct our scene. Linear transformations are also known as linear mappings or linear functions. They transform a vector space V into another vector space W while preserving addition and scalar multiplication. Or we could say that they are preserving the linear combinations of vectors. So if we have a linear combination of two vectors, so one vector u is multiplied with some scalar alpha, and we add to it some other vector v that's multiplied with a scalar beta, and we apply some kind of a function to it, then it would be the same if we were to apply that function on the vectors u and v, use the scalar factors on the results and add them together. So it doesn't matter if we're doing the linear combination in one space or another space, the result will be the same. So in 3D, of course, the scalars will be real numbers and vectors will be three-dimensional vectors. In 2D, they would be two-dimensional vectors. So let's take our vector space of points. So we have a vector space, two basis vectors. Let's have a point here. So point at coordinate 2 and 1. So 2 in x and 1 in y. And we can try out different mappings. So for example, the first mapping would keep the point the same. So it's an identity mapping. But we could have other mappings. So they could multiply one of the coordinates by 2, or maybe both of them, or with some other scalar. And you can try out the linearity of these mappings yourself. If you just take a linear combination of two different points and try to apply the mapping before a linear combination of those 2 points and after, and see if these mappings that at the moment multiply one of the coordinates with 2, are they linear or not? Now, from your algebra class, you might remember that all linear transformations can be represented as matrices. And the reverse is also true. Every matrix also gives you a linear transformation. So if you have a matrix vector multiplication and there are scalars in the matrix, this is a linear transformation. Or if you have a linear transformation, you are able to construct a matrix that does the same operation. Now, when we're talking about matrices and vectors, it's important to know which way we're storing them. So there are two storage orders. One is a row major order, another is a column major format. So different libraries and APIs use different formats. In our course, we'll be using the column major format, where the vectors are represented as column matrices, and the matrices will be multiplied from the left with the vector. This is standard in OpenGL, WebGL, Vulkan, and Blender, but row major format is also used, for example, in DirectX and Maya. And very often, when you're working with different libraries and technologies, you are expected to, guess or know or find out which format is used based on the context you're working in. So coming back to those linear transformations we saw before. So can we derive a matrix for these transformations? So let's try it with our transformation tree that multiplies the second coordinate by 2. But before we do that, we should remember how did matrix vector multiplication work. So let's say we have some kind of a function that we want to represent as a matrix vector multiplication. So you should remember how are these values in the matrix multiplied with the argument coordinates so that you will get the result. And they're done like this. So we take the first row and this entire column, and we make a linear combination out of these. And this will be the first element here, or the result, the first row of the result. So we take a times px, and we add b times py. And this is going to be the first coordinate of the result. For the second coordinate of the result, we just take the second row. So second row, and we kind of move these rows and turn them on top of the vector. And this is how I like to imagine it, so that we kind of move it on top of the vector and we combine those two vectors linearly, and this is the result. So now that we know this, we can very easily find out that in order to multiply the second coordinate by 2 and leave the first coordinate as it is, we want to put 1 and 2 on the diagonal of this matrix and zeros otherwise. Because it is exactly this matrix that gives us 1 times px, which we want as the first coordinate of the result, plus 0 times py. So we don't want any py added to the first coordinate of the result. It's just px. So this will be just px. And then the second row multiplied with this vector will give us 0 times px plus 2 times py, because it's 2 py, and this gives us 2 py. So this will be the matrix that does this mapping. And you can try out the other mappings and find the matrices for these other three mappings that we saw before yourself. It's not that difficult. So from this video, you should now understand linear transformations. They preserve the linear combination in those spaces that they transform between. You should also be able to test the linearity of a transformation. So given some transformation, you should be able to prove if that transformation is linear or not. And you should know that all linear transformations have matrices, and all matrices correspond to linear transformations. You should also know about matrices now, and distinguish between the row major and column major storage order, and know which one of these we use here. And if you come across another API or another technology, then make sure to find out which storage order they are using. And very importantly, you should know matrix vector multiplication. So this operation that we did here, where we multiply a vector with a matrix by just combining the rows with this column of the vector and getting the coordinates of the result that way for both rows, both coordinates of the result. This is going to be very handy in the following material.